Will be our last topic, current electricity. This focuses on Ohm's law and resistances in series and in parallel connections. Okay, so Ohm's law defines the relationship between the current, voltage, and resistance. So the current in the circuit, which is current I, represented by I, is equal to the voltage applied to the circuit divided by the resistance of the circuit. So that is I, current I, is equivalent to voltage all over resistance. The resistance of a circuit is equal to the voltage applied to the circuit divided by the current in the circuit. So that is the resistance of the circuit is equivalent to the voltage applied all over the current of the circuit. And the voltage applied to a circuit is equal to the product of the current and the resistance of the circuit, and that is voltage is equivalent to product of current and the resistance of the circuit. So the Ohm's law equations can be memorized and practiced effectively by using an Ohm's law circle. So voltage on top, current and resistance on the bottom. Okay, by simply, okay, let's say if you're going to solve for current, if the unknown is current, voltage is given, and the resistance is given, you can simply cover I, and as you can see, voltage is on the top and resistance on the bottom. So I is equivalent to V all over R. Similarly, if you're going to solve for voltage, provided current and resistance are given, you can simply cover V. And as you notice, IR, okay, can be a product. So voltage is equivalent to I multiplied by resistance. And solving for the resistance, if voltage and current are given, you can cover R. Okay, as you can see, V all over I. Okay, so that can be summarized as this one. Okay, covering I gives you V all over R. So notice here. Then resistance covering R, as you can see, voltage all over I. Okay, and covering for voltage, that is solving for V, is equivalent to IR. Okay, you can use this Ohm circle if you want. So power is defined as the rate of change of energy with time. The derived unit of power is joule per second, which is termed as watts. So power can also be written as work or energy per unit time. Okay, so joule per second, and that joule per second gives you the unit watts. And if current, voltage, and resistances are given in the circuit, okay, so you can use this formula. So that is voltage multiplied by current, and the unit is watts. Okay, so from this formula, okay, P is equivalent to VI. Okay, you can either use Ohm's law. Okay, you can substitute value of I being V. Okay, the value of V is IR, so you can say that this can also be equivalent to IR, which is V, voltage multiplied by I. Okay, so that gives you I squared R. And similarly, if you're going to substitute the value of I from Ohm's law, which is V all over I, so that gives you power is equivalent to voltage, which is V, okay, and I is equivalent to V all over R, and that gives you V squared all over R. So that gives you I squared R, okay, and that is also V squared R. So this can be used as the formula for power. Okay, depends on the given. Okay, now let's say illustration problem 13.1. Determine the current that will flow in a 10 ohm resistor that is connected across a 50-volt source battery. How much power is delivered across the resistor? So the given are 10 ohm resistor and a 50-volt uh, source battery. So the resistance is equivalent to 10 ohms and voltage is equivalent to 50 volts. So the required are the current that will flow in the 10 ohm resistor, which is I, and the power delivered across the resistor. So I is unknown and power is unknown. So using Ohm's law, based on the given voltage, resistance, so unknown is current. So simply I'll just cover I. Okay, if I'm going to cover I here, I'll have I is equivalent to V all over R. Okay, that's my formula now. Now substituting the numerical values, voltage is given as 50 and resistance is 10. Then dividing those values, that gives you 5 amperes. So the current that will flow in a 10 ohm resistor is 5 amperes. Now, how much power is this delivered using the formula for power? Okay, based on the given, I have used this formula, V squared all over R. Okay, so substituting the numerical values, that will give you 50 squared divided by 10. Okay, and that gives you 250 watts. You can also check, okay, using the other formula for power by using I squared R or uh, VI. Okay, so voltage is 50 and current is 5 amperes. Okay, so product of this gives you 250 watts. And for power, I squared R for the other formula, that is current squared multiplied by resistance. So current is 5 amperes, then squared multiplied by 10. 25 times 10 is 250 watts. Illustration 13.2. Okay, determine the current and resistance. Okay, current and resistance. Okay, across an electric heater that consumes 1200 watts when connected across a 220 volt source. So the given power is given, okay, 1200 watts, and the voltage or source voltage is 220 volts. So the required are current I and resistance R. Okay, from the formula of power, okay, given, okay, voltage and power, so we can solve for current I. Okay, dividing both sides by I, that or V, I mean voltage. So voltage and voltage here will be eliminated, so that leaves you current I. So I is equivalent to power all over voltage. Substituting the numerical values, that gives you 1200 watts divided by 220 volts, and that gives you a current of 5.45 amperes. Okay, now solving for the resistance using Ohm's law circle. Okay, solving for resistance, I'll cover R because that is unknown. Okay, that will give me V or voltage all over I. Okay, voltage all over I, and substituting voltage 220 volts and the current is 5.45 amperes. So dividing those values, that gives you 40.37 ohms. Okay, alternatively, you can use for other formula for power, provided voltage is given. Okay, as you can see here, power is equivalent to V squared all over R. So you can simply solve for the resistance, and 220 volts and 1000 for 200 watts. You can substitute those values. Okay, 220 volts squared divided by 1200 watts gives you 40.33 ohms. Okay, slight difference from the previous value. Why? Because 5.45 here, okay, isn't this isn't the exact value. It has a 45, 45, and so on. So if I just put 45, another 45 here, that will give me 40.33, approximately similar to this value. Okay, if I have solved for R, then I can use Ohm's law, okay, to solve for current. Okay, upon checking, okay, you can check if, yeah, those values are correct. Okay, so from the formula, power is equivalent to I squared multiplied by resistance, and the current is 5.45 multiplied by 40.37, and that gives you an approximate value of 1200 watts. So illustrative problem 13.3. So the current in the ammeter reads 20 amperes. So ammeter, okay, is an electrical device that measures current in a circuit. Okay, ammeter is connected in series. Okay, so the current in the ammeter reads 20 amperes while the load is connected across a 230 volt supply. Determine the resistance and power delivered to the load. Okay, so the given are current and voltage. Okay, so the unknown values are resistance and power. So you can solve for resistance using Ohm's law circle. Okay, so the unknown is resistance, so I'll cover R. Oops, so I'll just cover R. Okay, I'll just cover R for the unknown. Okay, so that gives me V all over I. Okay, substituting the numerical values, voltage is 230 and 20 amperes for I. That gives me an 11.5 ohms resistance, I mean. Okay, so the resistance of the load is 11.5 ohms. So power is equivalent to voltage multiplied by current. So substituting the numerical values, that gives you power is equivalent to 230 volts multiplied by 20 amperes, and that gives you 4600 watts. Okay, so our next topic is resistances in series. So the main characteristics of a series circuit, okay, are as follows. Okay, now in series circuits, resistances are connected in series when they are connected from end to end. Okay, and there is a continuous path. Okay, as you can see here. So there are no intersections. Okay, so circuit is continuously uh, uh, continuous connection. Okay, there are no intersections in between. Okay, or similarly, okay, similarly, this can also be written as, this is a resistor, for example, then another resistor here, okay, and then another resistor here, then this will be the voltage source. Okay, as you can notice, okay, this is this circuit from the picture and the circuit I have drawn. As you can see, if you're going to walk across this, there's a continuous path. Okay, no intersection. Okay, this is called series connection. And in series, same current I flows through all the parts of the circuit. That is, if I have current I here, okay, so if I have a current I here, okay, and that current will flow in the circuit, okay, it will continuously flow here, then going here, and passing through resistance 3 and going back to the voltage source, then continuous flow. Okay, similarly on this portion, okay, if this is the movement of the current I, okay, uh, so the current that will pass through resistor 1 is equal to the current that will pass through the resistor 2 and the current passing through the resistance 3. So the total current that will flow across the circuit is equal all throughout the all through the all the parts of the circuit. So I could say that the total current I is equivalent to the current passing through resistance 1, which is I1, and equal to the current passing through I2, which is I, and current passing through resistance 3, which is I3. Okay, so for number 2, voltage drop across each resistors are additive. So voltage 1, voltage 2, voltage 3. Okay, so these are the voltage drop across each resistances. Okay, and they are additive to give you the total voltage. Okay, they are not uh, always equal. Okay, V1 is not equal to V2, and I could say that it is also not equal to V3 because of their different values of resistances. Okay, uh, V1, V2, V3 can be equal in the series connection when the resistances have equal values. Okay, but we have assumed that they are not equal, so V1 plus V2 plus V3, which is this one and the other one, will be equal to the total voltage. Okay, same goes, resistances are additive, so the total resistance of the circuit will be equal to resistance 1 plus resistance 2 plus resistance 3. So these are the three main characteristics of the series circuit. Okay, so let's have this problem. Determine the total current and voltage drops across each resistor in the given circuit below. Okay, also determine the power delivered across each resistor. All resistances are in ohms, so resistances are 2, 4, and 6 ohms. So 2 ohms, 4 ohms, and 6 ohms. So determine the current, okay, across each resistor and the voltage drop V1, V2, and V3. Okay, so since they are connected in series, we could say that the current I, okay, the current I that will flow here will be equal all throughout. So if current I flows here, then current I will be equal to I1, will be equal to I2, and will be equal to I3. Okay, this is one of the characteristics of the series connection circuit. Okay, so using Ohm's law circle, so given our resistances and voltage, okay, so resistance are given, voltage are given, you can solve for I. If I cover I, that gives me V all over R. Okay, now solving for R, okay, so you need total resistances. So resistances across series connection are additive, right? Solving for the total resistances, so that gives me total resistance R will be equal to R1 plus R2 plus R3. Okay, they are additive, so R1 is 2 ohms, R2 is 4 ohms, and R3 is 6 ohms. So 2 plus 4 plus 6 gives us 12 ohms. So this is the total resistance of the circuit. Okay, so this circuit has been simplified to a circuit similar to this one. Okay, since the total resistance is computed, these resistances are combined to a single resistor which has a value of 12 ohms, and this becomes 12 ohms. And the voltage applied is still similar, which is 24 volts. Okay, so this is the simplified circuit, and the current flow I will flow in the circuit. Okay, now applying Ohm's law. Okay, from I equals to V all over R, so that is the voltage. Total voltage is 24 volts divided by the resistance, which is 12 ohms, and that gives us 2 amperes. Okay, these 2 amperes now will flow across the 12 ohm resistor. If these 12 ohm resistor are the combined resistances of 1 and 2 and 3, so the 2 ampere current will flow here, all throughout the circuit. Okay, thus the current across the resistor 1 will be equal to the current across resistance 2 and resistance 3, and that is equal to I. Okay, so the current across each resistors is 2 amperes. Okay, now the voltage drop, solving for the voltages across each resistor using Ohm's law circle. So if I'll cover V, this is the unknown, that gives me V is equivalent to IR, right? Okay, so that is for the voltage 1, or voltage across the resistor 1, which is V1, V2 for resistor 2, and V3 for resistance 3. We will be using this formula, that is for V1, so that is I1 multiplied by resistance 1, and I1 is equal to I, which is equal to 2 amperes. So 2 amperes multiplied by resistance 1, which is 2, and that gives us 4 volts. Okay, similarly for voltage 2, therefore this is I2 and R2. So current across resistance 2 is simply I, which is simply equal to 2 amperes, and resistance 2 is 4, so 2 multiplied by 4, 8 volts. Similarly with voltage 3, okay, across resistance 3, I3 is 2 amperes, resistance 3 is 6 ohms. Okay, so 2 multiplied by 6, okay, that gives us 12. Okay, so the voltage across resistance 1 is 4 volts, voltage across resistance 2 is 8 volts, and voltage across, oops, this is 3, sorry, and this is also 3. So voltage across resistance 3 is 12 volts. One of the characteristics of the series connection, uh, voltages are additive, right? So if I'm going to add all these voltages, okay, so 4 plus 8, that gives us 12, plus 12, that gives us 24 volts. Okay, resistances in parallel, okay, as shown in the circuit. Okay, so from this circuit also parallel connections. Okay, so if I have here, okay, this one a resistance, then another resistance R2, and this is R3. Okay, so in parallel connections, okay, resistances are connected from each of their nodes. Okay, okay, so there is no continuous connection flow of current here. So if a flow of current I, passing through here. Okay, that current I will intersect through or pass through this node, and this node splits the current into values. Okay, and this gives me I1 for resistance 1 as shown here. Okay, and this current now will be again split into this current. So this is I2 for resistance 2 as shown here below, and this now becomes I3. Okay, I3. Okay, passing through here. Okay, and it comes out with the total current I. Okay, so if this current I passes through this node, okay, it will be split into three currents, I1, I2, and I3. Okay, and they will be again meet at this other end node. Okay, if this is I1, this is I2, and this is I3. Okay, when they comes out here, they become the total current I. Okay, so the main characteristics of a parallel circuit is same voltages acts across all parts of the circuit. That is voltage, total voltage V will be equal to V1 here, will be equal to V2, and will be equal to V3. If voltage applied is V, so from this node and that node, okay, this gives us a voltage V1 for resistance 1, but V1 is equal to V, okay, as stated here. Similarly, okay, on this branch, okay, there's a voltage here V2, okay, but V2 is equal to V as stated here. Okay, similarly, this is V3 for R3. Okay, resistance 3, voltage 3 will be equal to V. Okay, so all throughout across the parts of the circuit is equal voltage V. Okay, branch currents are additive, which is current total current I is equivalent to I1 plus I2 plus I3, which is I have stated here. Okay, I1, then I2, and I3. Okay, they meet on this node, then comes out as a total current I again. Okay, then comes back through this node, then becomes split, will split to 3. Okay, it is not divided into 3, okay, equal value. It's not like that because different resistances are applied. Okay, so the total resistances may be computed using this formula. Okay, don't forget these formulas. So there is the reciprocal of the total resistance is equivalent to the summation of reciprocal of individual resistances. Okay, so let's have this illustrative problem 13.5. Determine the current across each resistors and power delivered across each resistors. Also determine the total current and total power in the circuit. Okay, so the given, okay, this is the one of the characteristics of parallel connection. Okay, voltage across the circuit is equivalent to the total voltages, so 120 volts, that is the total voltage source. Okay, so the voltage across this 50 ohm resistor is also 120 volts. Same goes here, 120 volts, and that is also 120 volts. So this is 50 ohms, 500 ohms, and that's 550 ohms. Okay, let's say this is R1, R2, and R3. Okay, using Ohm's law, okay, determining for total current. Okay, if I cover I'll have V all over R, right? I is equivalent to V all over R. Now, solving for the total resistances, recall for parallel connection, reciprocal. Okay, 1 all over R is equivalent to 1 all over R1 plus 1 all over R2 plus 1 all over R3. Substituting the values, okay, R1 is 50 ohms, R2 is 500, and R2, 3 is 550. Then solving for R, okay, that gives us this equation. Okay, now simplifying that using the calculator, that gives us a value of 41.98 ohms. Okay, now applying Ohm's law to solve for total current. Okay, the total current of the circuit I will be equal to 2.86 amperes from this equation. So I is total voltage all over total resistance, which is 120 volts divided by 41.98 ohms. Okay, now the total power of the circuit will give us this value, 343.02 watts. Okay, so let us double check that value. Okay, so 120 squared divided by 120 squared divided by 41.98. Okay, so that gives us 343.02 watts. Okay, since the voltage across each resistor is 120 volts, okay, so the current on each resistances is gives you this value from this equation. Okay, so I1 is equivalent to V1 all over R1, but V1 is 120 volts and R1 is 50, right? So that gives us 2.4 amperes. And for I2, so V2 is equivalent to 120 and R2 is 500. So substituting then gives us 0.24 amperes. And for I3, so 120 volts divided by 550, which is R3, so that gives us 0.22 amperes. So if I1 flows here, then that is 2.4, then I2 is 0.24 and I3 is 0.22. So if they will all come out here again, okay, so I1 plus I2 plus I3, that gives us this value. That becomes I again, right? Okay, now the power on each resistor will be equal to power at resistance 1 V squared all over R. Okay, using this formula. So voltage is 120, resistance 1 is 50, then that is 288 watts. Then for power 2, 120 volts squared divided by 500, so that's 28.8 watts. And that is for power 3 under resistance 3, so 120 volts squared divided by 550. Okay, if you're going to total these values, that will give you this total power of the circuit. Okay, problem 13.6. So determine the current that will flow in each of the resistors when the circuit is connected across a 250 volt source. Also determine the power delivered across each resistor. So we are determining the individual currents that will flow across the 2 ohms, 50 ohms, 25 ohms, and 50 ohms here, and the 8 ohm here. Okay, and also determine the power delivered across each resistor, that is the power that will be delivered on the 2 ohms, on the 50 ohm, 25 ohm, 50 ohm, and 8 ohm resistors. Okay, so analyzing and simplifying the circuit. So based on the circuit, 2 ohms, 8 ohms. They are connected to a parallel combinations of resistances, which is 50, 25, and 50 ohms. These three resistors are connected in parallel. Okay, so we are always starting at the end of the circuit going to the source. Okay, now since the 50 ohm and 25 ohm and 50 ohm resistors, these three resistances, okay, they are connected in parallel. Okay, so using the formula, okay, so 1 all over R will be equal to 1 all over R1 plus 1 all over R2 and so on. So recall that formula. So substituting the values, we'll have 1 all over R will be equal to 1 all over 50 ohm plus 1 all over 25 ohms and 1 all over 50 ohms. And that gives us this value solving for R. Okay, that value will become 12.5. Now, upon simplifying these three resistances, 50 ohm, 25 ohms, and 50 ohms, the circuit now will become in this state. Okay, so this is the 2 ohm resistor, and this will be the 12.5 ohms, and this is the 8 ohm resistor. Okay, and this is the source voltage of AB, which is equivalent to 250 volts. Okay, so when these three resistances are combined to a single resistor, so the value of that resistor is 12.5, and that becomes, the circuit becomes in series, right? Okay, now so the 2 ohm, the 12.5 ohm, the 8 ohm resistors are now in series. Okay, so since they are in series, so solving the total resistance of the whole circuit, that gives us 2 ohms plus 12.5 ohms and 8 ohms, and that gives us a value of 22.5 ohms. So total resistance of the circuit becomes a single resistor, and that value gives us 22.5 ohms. Okay, so these three resistors are combined to a single resistor which has a value of 22.5, and that is connected across a 250 volt source. Now, solving for the total current of the circuit using Ohm's law circle. Okay, so unknown is I, which is the current. Okay, so voltage all over R. Now the total current is voltage or total voltage all over the total resistance. So total voltage, that is the voltage supplied, which is 250 volts all over the total resistance of 22.5 ohms. And that gives us a total current of 11.11 amperes. So that 11.11 amperes will flow across this resistor. Okay, this is the I total. But then if we are going to back to the previous circuit, this is the circuit, right? Okay, so the total current I, or I total, will be equal to those circuits. So the current that will flow through the 2 ohm resistor is 11.11 amperes. Same goes with the 12.5 amperes ohms, 11.11 and 11.11 amperes. Okay, for the 8 ohm resistor. So the total current of the circuit is given as 11.11 amperes. So recall. So the circuit is has 2 ohms, and this is the 12.5 ohms, and also, so this is the 12.5, and this is the 8 ohms, and this is the 2 ohm resistor. Okay, so the current, okay, in series connection, I total is equivalent to I1 will be equal to I2, and that will be equal to I3. Okay, so if they are connected, the current that will flow is 11.11 amperes. Okay, the power delivered now in the 2 ohm and 8 ohm resistor, okay, the 2 ohm and 8 ohm, using the formula power I squared multiplied by R. So for power 2 ohm resistor, so 11.11 squared multiplied by 2, that gives us 246.86 watts. And for the 8 ohm resistor, 11.11 amperes squared multiplied by 8, that gives us 987.46 watts. Now, we cannot solve for the power of uh, the, we will not solve the power across the 12.5 ohms. Why? We don't need the power delivered across this resistor because we are solving for the power delivered across the 50 ohms, 25 ohms, and the 50 ohms. So we can simply solve for the voltage drop across this resistor, and that voltage drop will be equal to the voltages across these three resistors because they are connected in parallel. So solving for the voltage across the 12.5 ohm using Ohm's law, if I cover V, that gives me IR. So voltage will be equal to IR. So voltage across the 12.5 ohm is 11 point 11.11 amperes multiplied by, oops, this is 12.5, sorry, this is 12.5. Okay, so solving for that, that gives us 138.875 volts. So the voltage drop across the 12.5 ohms is 138.875 volts, and that voltage is also equal to the voltages across these three resistances. So voltage drop across the 50 ohm is 138.875 volts. Same goes with the 25 ohms and also the other 50 ohm resistor. Okay, so the voltage across the 12.5 ohms is 138.875, and that gives us the voltage across. Okay, reminder or recall the voltage across the circuit uh, is equal to the total voltage for what? Parallel connected resistances. So V1 represents 50, so voltage across the 50 ohm. V2 will be the voltage across the 25 ohm, and V3 will be the voltage across the 50 ohm, the last resistor, which is a 50 ohm resistor. Okay, now the current across the two 50 ohms and, okay, the 250 ohms, the last resistor, the third, and this one, okay, and the 2 ohm are the 25 ohm resistors are, okay, using Ohm's law circle. So solving for the current, I'll cover I, that gives me V all over R. Okay, now current across the 50 ohm resistor, which is 100 voltage all over R. Okay, so 130.875 volts divided by 50, that gives me a 2.78 amperes. Okay, now solving for the current for the 25 ohms, that gives me voltage all over R, that is 138.875 volts divided by 25, that gives me 5.56 amperes. Now for the last resistor, which is 50 ohms, okay, similar to this value, so that gives you uh, current on the last resistor, which is 50 ohms, is voltage all over resistance, which is 138.875 volts divided by 50 ohm. ohms, that gives us a similar value of 2.78 amperes. Now, the combined resistances of these three resistors is 12.5 ohms, right? Then, if you're going to total these three resistances, okay, this gives us an approximately equal to 11.11 amperes, okay, of current. And that is similar to the current that flows through the 12.5 ohm resistor. Okay, now the power delivered in the 250 ohms, which is this one and that one, the last resistor, and the 25 ohm resistors are okay, using this formula. Oops, this is power, which is P. Okay, power is equivalent to I squared R. Okay, so power across the 50 ohm, which is I squared 2.78 amperes squared multiplied by its resistance of 50, that gives us a 386.42 watts. And for the 25 ohm resistor, so the current that flows on that resistor is 5.56, so 5.56 amperes squared multiplied by 25 ohms, that gives us a power of 772.84 watts. Okay, and for the 50 ohm resistor, the last resistor, okay, similar value for this one, that is 386.42 watts. Okay, so the currents across each resistors are solved. Okay, and the power across each resistances are already solved.